All right, folks, welcome back. This is Tuesday, the 26th of March. Last week, we covered convolutional neural nets. This week, we'll finish that topic and we'll go on um, uh, to a new neural architecture called autoencoders. So we have a busy day. I hope you brought your fresh minds to work today, to our classroom today, and we're going to talk about it. So first, a quick recap of what convolution is. Intuitively, if you recall, we said convolution is like having a tiny window to look at. You're not looking at the world in a far or wide view. Right? It is like you're looking through a tiny window. One way to think about it is that you use a very narrow beam telescope. Right? So when you look at the sky, right, you can do either deep space photography. Those of you who are into photography, you can use a big zoom lens, isn't it? Or you can look at the sky, or you can look at the nature. What do? When you zoom in, you get a very tiny slice of reality, is all that is visible in your window, isn't it? Now, if you take the photography metaphor, those of you who are used to, do you know what f-stop is? Aperture? What happens when you open the aperture of a telescope wide or of a lens wide?
More light comes in.
More light comes in. What does it do to the depth of field? It becomes you get, see, one of the things that happens is you get a very narrow depth of field, f-stop, right? At f, for example, f2.8 or how many of you, by the way, are into photography and know what I'm talking about? Some of you. Okay, so what happens is that there's something called a depth of field. Have you seen pictures in which only for example, a model or a child is visible and the background is blurred? Right? That is called a very shallow depth of field. The whole camera is focused just on that person, right? Even though it sees the surrounding background, even though it's visible in the lens, it manages to eliminate that or make it sort of smooth, right? That is one intuition you can carry about convolution. What the lens is effectively doing is it's convoluting over the reality. The reality is much bigger. You're looking at a very narrow window of it. And even then, you're sort of picking up certain very narrow thing, like, for example, that child. That is one simple intuition you can carry about what a convolution does. So convolution filters, these things are also called kernels. The word are interchangeable, kernels. Some books will call them kernels. Some books will call them filters. Let's call them filters, because filters is something we are all familiar with from Photoshop and especially if you are into photography. And when we deal with convolution, because they have a huge impact in vision systems, computer vision systems, in images and videos and so forth. So you will often see that the traditional language of visual imaging dominates the vocabulary of convolutional neural network. Filter is a more intuitive word than to speak about a kernel, right? This function, and so let's look at this. We said that if there is a function fx, what we can do is we can bring in this orange thing, gx, which sort of is like that, very narrow field of view, isn't it? It has a very narrow field of view. And in fact, it peaks its attention, or its focus peaks in the center. It's somewhat like your lens with a very shallow depth of field and a big zoom, isn't it? That's what it is. So the formal name of GX is, it's a kernel. Right? In our world, we call it, basically we call it just a filter. Right? Because a filter is so photography or visual thing based, the intuition carries forward very much. We talked about this, that you can use that to go all over the image and pick it up and pick up. Each filter is looking for something. One is looking for edges, one is looking for a horizontal edge, one is looking for a vertical edge. Each one of them is looking for something. And what people would do is they would scan the image with a filter and pick out all the places that they would find what they were looking for. For example, a horizontal line detector would scan all over the picture and say, oh, I found it here, I found it here, I found it here, isn't it? That sort of things. And so there was, before deep neural networks came out, there was a cottage industry of people coming in computer vision. For example, when I did computer vision way back in the 90s, right, there were libraries of filters, and there were research papers saying this collection of filters is better than this collection of filters. Right? They were hand-created filters. They were deeply created from experience over the real world, empirical world, and people would sit down and create the best filters with which you could drive computer vision. Okay? Remarkably, even in those days, computer vision was making a lot of progress. In fact, I was at the University of Illinois, Urbana-Champaign, and the computer vision group had already created and we're talking of 90s, a car that could self-drive from Urbana-Champaign all the way to Los Angeles with a very small 1 or 2% human intervention. Right? And, yeah. And the tricks it used us quite interesting tricks, actually. What we would do is a car is going forward, like you're following, and so you're looking for road lines on the road. But when the lines on the road would disappear on the highway, it would start looking for the back of other trucks because you would get parallel lines and just start following that. Right. And then occasionally, now 1 or 2% human intervention is quite a bit of human intervention, right? But the fact that you could get away with that in the computer vision that we guys were doing in those days just speaks of how mature the field had become even then. And then with the sort of filters and the kind of technologies that we are doing. So it just goes to show that simple ideas can take you very far. Then came deep learning, deep neural networks. What does deep neural networks bring? One of the realizations with deep neural networks was that these class of algorithms, so in those days, this some of the state-of-the-art algorithms for computer vision and etc. were things like support vector machines. So now you guys know where this name of my company comes from, support vector machines. Right? It's a beautiful algorithm. In a course, in a separate course, I used to teach this, and it is heavily used in the medical field even today. It's still there. Now, it turns out that actually the support vector machines are a realization of something called kernel machines. And it turns out that neural networks are actually kernel machines. Not many people realize that neural network is something, is in a way a kernel machine. And they use something called neural tangent kernels. So there's a lot of interconnectivity in mathematical ideas in this field, how ideas mature and how we grow. Having said that, the deep neural networks, they have a quality that we are only beginning to understand why it happens. No one fully understands it. But to the extent that we do, what we find is that classical machine learning algorithms are there, as you make them bigger and bigger, their accuracy, their AI performance saturates. So you see this orange curve. They have an asymptote, they plateau off. But the point with deep neural networks is that actually they underperform with small data, right? But very quickly you reach an inflection point at which they start beating the traditional algorithm. And then, for reasons that we don't quite understand, they keep doing better and better and better. Right? The more data you throw at it, the more complex you make it, the better their performance becomes. They don't saturate. Are we together? They just don't saturate. Now, with that being there, now we will come to, I would like to start today's discussion with a question that Sushinda asked while some of you were here and others were still walking in. Sushinda asked this question. Let's look at the MNIST dataset. MNIST dataset is the handwriting dataset to vector recollection. 0 to 9 digits. There are 50,000 samples for training and 10,000 samples that you can use for test, something like that, right? Images. These are 28 by 28 pixel images, black and white, simple, as simple as it gets. It has been a benchmark to test how well different algorithms work. And it has been a tradition in machine learning to say that, people bring different theories, different models, using wildly different theories. Now, the field is so vast that nobody has the time to go read all the theories. But let's put up a benchmark to measure all those things with. So, with the spirit that the proof of the pudding is in the eating, what you do is you bring all your fancy theories, but at the end of it, a proof that you can achieve the state of the art performance. Right? And so people tried, the MNIST data said, long history of people gradually trying to improve it. When deep neural networks came out, um, especially when the convolutional came out, before that, the state of the art accuracy actually did belong to support vector machines. The accuracy was, if I'm right, about 23 or 26% error rate. Right? You still had a pretty significant error rate. And then when the CNN came out, I think even in the very first iterations, they brought the accuracy down to the error rate down to 16%, 13%, and within no time, the error rate went down to below 1%. Now it is like 99 point something accuracy. It's practically, and the errors are so low. If you look at the situations where it got wrong, those by no valid definitions would be considered digits by anybody, right? They're just squiggly marks that somebody labeled as a digit, right? So obviously the CNNs have achieved perfection. So now this question that I will ask you, that Sushinda asked, and let's see what answers we get from the audience. He asked a deep question. He says that suppose I create a multi-layered neural network. They are universal approximators. Just stack many of the layers together, make each layer rich enough, throw in activation function. Why can I not achieve state-of-the-art accuracy on the MNIST dataset? Why does CNN beat it? Why does convolutional networks beat it? So how would you like to answer that question? Go ahead.
So the main problem in the bitmap in this data set is basically, when you write something, there is a correlation between the pixels, and the correlation actually forms lines, curves, and stuff that actually forms the number.
Yeah.
But if you use a regular neural network, there's a technical term for it. I forgot about it. But the relationship correlation between the pixels is lost. Just use it as a bunch of pixels.
That is right.
If we use a CNN,
yeah,
we actually are able to get the lines and curves and certain formations.
That is right.
That makes it more precise.
Yeah. Very good. Yeah. In a way, you're getting. But so anybody else would like to say it differently?
All I can remember is there's a different filters, and then that filters give you different perspectives of the image.
Right. That's right. It's a paradox. Yeah. Okay. So what I'm hearing is that there are filters, and filters somehow do better. But why do they do better?
But in this, you are showing only one numbers, right?
One digit, yeah.
Multi we can give that?
Well, but in theory, of course, if you can get it right for one digit, you can get it right for more compositional properties.
In the page 28 by 28,
just one digit.
1 and 2,
yeah.
It's got recognition.
No. You have to give only one digit. The data set by nature, by construction, is single digit.
But in CNN, we can give a one mountain, trees,
multiple things you can give. That's an aspect, yeah. But focusing back to just MNIST, why did CNN do better than just a feed-forward network for MNIST?
So Asif, the question specifically was. CNN is a special case of a neural network, right? So that
is a special case of a neural network. Yes, it is in some sense.
Mm-hmm. So I just
yes and no. Can it be called a basic special case of a feed-forward network? Think about it. How many of you can argue that a filter, at the end of the day, is a special case of a feed-forward network? Or can you formulate it? Can you lay out a network and hand set its weights in such a way that it essentially behaves like a filter? So, anybody remote would like to, anybody on Zoom would like to give it a try?
So I think you have it on the screen right now. Translation, equivariance, local structure, hierarchy.
Yes. And who is saying this?
Ravi.
Oh, yes, of course. Thank you. Thank you. I literally had the answer in front of you and was waiting for somebody to read it out. Right. See, guys, the word is inductive bias. Right? See, a deep neural network, a feed-forward network, and is a generalized network. It makes no inductive bias, no presumptions about the external reality. Are we together? So what happens, and Sashinda, for you, your point is true. A filter can be thought of as nothing but a special feed-forward network with the constraint that certain weights repeat themselves in the layers. Like between the layers, certain weights repeat themselves. Right? So there is weight sharing. That's why you say that filters induce a weight sharing as when you look at it from the point of view of a feed-forward network. But the fact that you can force that weight sharing, you may ask, a generalized neural network would not do weight sharing. It would say every weight is independent. When you pin it down like that, when you give filter weights, it begs the question, why are you doing it? And the answer to that is, this is because you look at reality, and in reality, you notice that external reality has certain properties. And we observe this actually by looking at the slices of the cat's brain and how the eyesight, what the cat was seeing, was affecting the back of the brain, the activations in the brain. What we observed, right, was that certain areas of the brain were triggered only by certain parts of the image of the external world, the image that was coming in. And thus arose, from that, after a lot of thinking, people realized that there is something. If you're looking at the external world, suppose you're looking at a scene, and like we took the example of the scene, the sun could be here over the cloud, or it could be rising over the hill. Right? In either of the two situations, we would still recognize it as a sun. Right? So we need a device that knows the structure of the sun, right? And will recognize the sun anywhere in the picture. Are we together? Or will recognize a cat, whether it's on the table, whether it's on the floor, or whether it's on the windowsill. Does that make sense? Whether the cat is turned left or right, or is hanging or jumping, a cat is a cat. Right? It should recognize that. So when you think about that, the first thing so the property that comes to mind is it should have translation equivariance. Means if the cat moves from here to here, somewhere in the activation, there should be a wave of activation. In the final layers, just which neurons get activated should change, but the pattern of activation should remain the same. It just should translate. Are we making sense? Now, when you try to impose that in a completely free form or unconstrained neural network, it's a lot harder to do that. You can't do that. You can't impose translation equivariance. And the machine will not learn it well. It will, no matter what you try, it will only do a very, very vague approximation to it. Right? So by imposing it, you're in a way giving it new information. You're making the problem a lot easier. Like, for example, I did that, right? So I just said, okay, here's a text. Yeah? Where is it? This tree is there and this tree is here. We want the tree to be a tree, no matter what, right? So that's a translation equivariance. The other one is local structure. It turns out, and local structure and hierarchical structure are two qualities of the external world. Things are compositional. Right. So, this goes down actually to a lot of theories about, well, this is a little bit of a tangent. If you look at the philosophy of knowledge, the theories of knowledge, you'll realize that people take many, many approaches to it. One of the things people often say is that knowledge is compositional. Right? So suppose you see something that you don't recognize. your basic mindset is to start breaking it down into components that you do recognize, isn't it? So, for example, if you go and see an elephant with two trunks, you haven't met an elephant with two trunks, right? Let's say there's a trunk in the front and there's a trunk in the back. Right? And so now you would say, well, it looks to me that our two elephants back to back have been co-joined. Something like that. You would understand it. So we tend to understand things from little structures we recognize, and then we sort of zoom out and we compose things out of it. Right? So it would be nice to have an architecture that imposed that inductive bias, which comes from external reality, that inherently somehow has two capacities. It first is local. So, for example, if you look at this eyebrow and a tiny patch of it, its information is also contextualized this. Now, this tiny patch could easily have been my mustache. But the fact that it is an eyebrow, its meaning comes from also the neighboring parts of the eyebrow, isn't it? So locality of reference or local structure is quite relevant in determining whether or not it is part of my mustache or part of my eyebrow. Well, actually, I don't have a mustache today, but imagine that I had. Right? So hierarchical structure. If you see a circle with two eyes and a nose on it, your first instinct is you're looking at a mammal, right? And teeth, right away, right? You're looking at a person, you're looking at a cat, you're looking at something. You're looking at a lion, you're looking at something. Does that make sense, guys? Right? So that is the hierarchical nature. So when you take these, so the more, see, there's a thing, in a way, you're helping the network by giving it partial answers, isn't it? You're guiding it how to look at the world. You say, assume that these things are true. So assumption-driven learning, assuming that those assumptions are true, are always faster and more accurate than context-free learning. And that explains, Sushinda, why CNNs tend to quickly converge and get it right. However, it does not negate the fact that you could still train a CNN to a fairly high degree of accuracy. So this is not the only trick we have. So, ideas keep coming. So for example, you can bring in the idea. There is an idea called residual. So ResNet, the history of CNNs is, and we'll go through some classical architectures that I'll ask you to study, and I'll give you a quiz on. But two of them, AlexNet 2012, changed the world. Right? The first CNN, the CNNs had changed the world, but no one noticed it. Jan LeCun's LeNet was doing handwriting recognition as a simple CNN, the simplest, purest CNN, exactly the way that I've explained it to you, was already changing the world. And today I'll give you the architecture of LeNet by doing handwriting recognition and having a revolution in the postal service and things like that. But the benchmark, the MNIST benchmark, the first convolutional network that made a dramatic shift was the AlexNet. AlexNet is a very simple network, but one of the things it has a small twist to it, but we won't go into that. Then came the idea, a very beautiful idea came out called residual connections or skip connections. What are skip connections is a slightly advanced topic, but I will introduce you to it. I'll give you the core idea, what skip connection is. Today, that's another idea. So people then applied skip connection both to CNNs and to feed-forward networks, and in fact, to every network that came afterwards. So for example, if you look at the transformer architecture, attention networks, you will always find the so-called residual or skip connections. Right? What are they? It's another interesting idea that comes up. And what that idea is that, see, every time you pass information through a feed-forward layer or any neuron, remember, activation function is there. What does the activation function do? It's a deformation machine. Deformation can be a force for the good or the bad. Deformation gives you the universal approximator. It gives you the flexibility. But what if the previous layer already had discovered something interesting, right? When you pass it to the next layer, right? Suppose the layer was in a state that it was doing a good job for one particular thing, right? But not for other things. So the next layer, by bringing in further deformations, might be doing overall better things. Right? So out of 10 things, it may improve on 9, but it may actually do worse on 1 or something like that. Are you understanding that? Right? So then what people realize is that if that's happening, let's do one thing. Every once in a while, let's short circuit the information forward. So you have the standard path. Every layer does its own deformations and activations and transformations. And then what you do is the information from a few layers ago, every once in a while, you give it a short circuit and add it to the information that has come through the Royal Road, to the mainstream path. And you add the two up. And you say, okay, the next layer need to take the sum of this and this. So what happens is that this layer is taking the transformed information, right? Transformed, deformed, linear transformed and deformed information, as well as the original information from a few layers ago. And why that is useful is sometimes some structure is better understood by putting the two together. I'll give you an example. In convolutional neural nets, I told you that each layer you do pooling. What does pooling do? The next layer will now look at a slightly bigger field of view, isn't it? So imagine that you're looking at a cat. So it's good. You went from the tip of the nose or the eyes of the cat, you zoomed out, now you're seeing the face. But one of the things you might be losing is maybe the beauty, the specific details and the roundness of the eyes or whatever it is, right? You might be beginning to lose that. So what can I do? If I short circuit that information and add it to the next layer, then I have fine-grained information as well as coarse-grained, zoomed out information now. Do you see that, right? I have a little bit more global structure as well as local structure from a few layers before coming and adding to it. Does that make sense? So, and would you agree that that would be a good thing, right? Because you're getting both now. You're getting fine-grained info as well as a little bit zoomed out info. To do that, that was the key breakthrough that made the ResNet architecture possible. What it did is it would do that. It would just hop across and add information from a few layers ago. Right? So that is it. Different scales, hierarchy of scales. You realize common sense tells you that go back a few scales, right? Take information here and there and bring it together. So that was ResNet, and it led to later on the evolution of one of the most successful image segmentation algorithms. We will cover that, called UNet. UNet. Those of you who are doing the Sunday boot camp, you will encounter, we will do that research paper in depth. But at this moment, time permitting, I will introduce it a little bit. I will introduce it at some point a little bit, but not in as much detail because we do cover it in the Sunday boot camp. It led to a very successful image segmentation framework. Because to recognize a cat as a cat, you sometimes need to know the bigger picture as well as see those eyes, bright eyes of the cat, isn't it? So that is that. So now, well, bringing that idea forward, the residual network is one. Now people can ask, why can't I use the same residual trick with feed-forward network? If you do that, feed-forward networks start doing better. Later on, as we learn about other architectures like attention, they become key ingredients to attention also, right? So the history of this field has been that over time, there has been an evolution of simple ideas. Right? One little contribution makes a huge difference. Then another little contribution comes, makes a huge difference, and so on and so forth. So everything seems to be getting better and better and better all the time. With that being said, CNNs is foundationally a huge improvement and a different idea compared to just feed-forward networks. Now, what is the typical architecture that you put? We'll talk about that. But before we do that, let me just continue to review. You have filters. In a neural network, what do you have? You have the linear transform, you have the activations, Now you have a lot of weights, but in convolution, you throw in just these filters. What do? Your filter is something that you impose upon the underlying data. You multiply it, each pixel by pixel, you multiply that value, and then you add it all up to see what comes out, right? And that becomes the value for that. You create a table, and that table is called the feature map. You fill up the feature map. Having filled the feature map, you do one more thing, and this is a place where we would get forward. A feature map is good, and after you have done a little bit of padding, etc., that we talked about, you would end up with a feature map that's about the same size as the previous image, except that each filter will produce its feature map, isn't it? So that begs the question, how many filters should I have? 1, 2, how many should I have? So here is something that has arisen empirically. What people have done is, suppose you have a cat. They would, this is let's say that this is just black and white or grayscale is the technical word, a grayscale picture. Right? What people would do, the original MNIST was this size. What people would do is that they would apply, let's say, a 3x3 filter. And if I apply padding, then what happens if I apply padding? You would, each of the filter, let's say F1, F2, Fk, they would create their own feature map. Okay? So you call these feature maps, so feature maps that it produces as a channel. The technical term people use is channel. They have produced information in, let's say, 3 channels. One channel is looking for edge, right? One is looking for horizontal line, one is looking for vertical line, as an illustration. Are we together? And so you will end up with a stack of channels. And why the word channels? It comes actually from image processing, because in reality, you can think of this image, if it was color image itself is thought of 3 images of a cat. One with a red filter, one with a blue filter, one with a green filter. And now you see why the word filter is so natural to CNNs. Right? What is a filter? Those of you who do photography, literally you take a colored glass. A colored glass is a filter. A red colored glass will only see red. Right? It will only see the red field, the red wavelength. The blue colored glass will only see the blue wavelength, and the green colored glass will only see the green wavelength. So technically, what you have now, generalizing beyond that, is that the cat, real world cat, image today, 2024, would come with at least 3 channels: a red channel, green channel, blue channel. So you will actually have 3 copies of the cat: red, blue, green, isn't it? Looking slightly differently. And we saw that with that cup. We saw 3 pictures. And so what happens is that when you apply these filters, F1 to Fk, you have to decide how many filters you apply and what's the result that you will get. Are we making sense, guys? Yeah. What's the result? So you get some filters. So you get the next set of feature maps. Now what you do, if I just apply another set of filters, another box of filters, that's not going to be very useful, because it turns out that filter is a linear operation. Why? Because what did we do? We did a product with the underlying information between the filter's weights. What did we do? We did the filter weight times the underlying information, right, plus whatever bias term you want to add. This is what? This is a linear transform, isn't it, guys? This is a basic linear transform, right? In fact, you did w dot x, right, etc. So this is a linear transform. Or you don't like linear transform followed by another linear transform, w1, let me just say x, b1, followed by w2 plus b2. Let's say that you apply this is your new x, you apply to b2, you realize will be w1, w2, x plus b2 plus b1 W2, right? This term. So what does it look? This is also a linear transform, isn't it? It is as though you multiplied by W tilde X plus B tilde being B2 plus B1 W2, this being W1 W2, isn't it? So you can't apply filter after filter. What is missing in between? What did we miss to do? The activation. So what you have to do is, after applying a feature map, and actually what people often say is that you do this filter convolution, then plus activation. So when you activate, it applies now a nonlinear transform. Are we together? So you say that one convolution operation, or one layer of convolution, or people also say one layer, is this, right? And you can apply, you can pick your convolution, ReLU or TANH, right? The work of Jeffrey Hinton and these people, all of these brought about the fact that it's a good idea to use ReLU, right? Are we together? Now comes an interesting fact. So that is good, but how do you zoom out? Remember, we want to have hierarchical information. We are not able to do that because we ended up producing a feature map at about the same size, assuming you're using padding. You may activate all you want, but you'll end up staying at the same level of granularity at which you're looking at the picture. Isn't it, guys? Right? It will just keep changing. So how do you zoom out?
Pooling it. No.
Yeah, so that brings up the pooling. The way you would do it in a lens is that what you do is you go back to that feature map. Let's say that this is feature map is really dense. And then you sort of do a low resolution or sort of a zooming out operation. So how do you zoom out? One easy way that you could do zooming out is just go and take this. Let me take this green. Take green. Take this. Look, pay attention to this. Now I create another different kind of filter. It is not your normal filter. Its only purpose is it will look at those 4 values, right? You can make it 4, whatever it is. 2 by here I'm taking 2 by 2. You can pick your size, and it will ask this question. I'm going to pick something that is representative of it, right? So, for example, if you have a black background and you are looking at white chalk, like for example, I'm doing here, and signal is white, what would be a good number? So suppose these numbers are, let's say 4, -1, 3, 2, or 3, let's say 12, 0. And I am trying to determine if there is some white marking here. What does this signify? In this region, there probably is white marking, isn't it? Right? Are we together, guys? There's a very pronounced signal here. So if I'm looking at white chalk on a black background, and that's all I care, one of the easy ways I can zoom out is by taking the max of the grid. And I say, hey, you know what? I'll take 12. I'll create a smaller thing, and I will again move this padding along. Yeah, I will move this padding along this, and then I can take another padding here. And from each of these, I pick the biggest of them. Does that make sense? Guys, am I making sense? Right. On the other hand, if I'm looking at black information on a completely white background, then what would make sense?
Smallest one.
Minus, negative, right? Because the whole thing is just white, high signal. The absence of light being lit up is the signal. Does that make sense? And so you would therefore you would preferentially take a min pooling, right? So a min pooling for black on white background.
They asked a question, but I don't know. How do I decide what pooling should I apply? So randomly.
We'll come to that. Come to that. Max pooling for white on black. Right. But suppose your signal is actually the midtones. Skin color is the midtone, right? And you want to focus on the skin tones like baby's face and so forth. Those, well, you might be better off using the average pooling, right, for such situations. So what happens is you can, but anyway, irrespective of what you do, what have you done? You have taken 4 information and reduced it down to 1. So you will end up a much smaller feature map. This will zoom down to literally a feature map 1/4 the size almost, isn't it? If you do it like this, 1/4 the size. Guys, am I making sense? And so now what happens is, if I again combine the next layer with the same 3x3 filter and run over it, this filter, when it is sitting here and it is filling up this space, it is filling up the space of the original image. How much of it is it covering? More of it, right? Do you see that? It is effectively zoomed out and it is looking at a larger receptive field of the original image, because each of these cells is populated by information coming now from a slightly more global, less local situation. So do you see the hierarchy of information being built up? Right?
It's basically an optimization of the iterations, because what we did beforehand is we took all of the data and did very large iterations, whereas using it and flattening it in a sense, the iterations are smaller and faster. And if we get the same reliability of results, you get the speed improvements.
No, that is not the reason. I mean, see, that happens to be a byproduct, but that's not the reason you mathematically you would argue for it. The reason for its existence is, if you think about it, look at the things that we wanted. We wanted an architecture with those which could induce a bias, which is translation equivariance and a hierarchy of features, and at each level, you zoom out, you have a slightly bigger receptive field. And if you argue with that thing in mind, you will realize that you cannot get away by having by dropping any one of those things. You cannot drop activation because then you are lost. The next layer is meaningless. You can't do a deep network, right? You can't drop filters because filters is the detector, feature detector, right? And through it, you get essentially the translation, the weight sharing of the translation equivariance. You wouldn't get that. And pooling is essential to increase the receptive field in the next layers. Are we together? The fact that this may expedite computation in subsequent layers happens to be a byproduct. Yes, you'll have smaller matrices to multiply, but actually that doesn't quite happen, because what you do is that at each subsequent layer, you bring in more filters. Are we together? So remember that, so think of it like this. So now our theory, okay, before I go into that, let's see. So now what are the 3 core ingredients that we want in every convolutional layer? So you realize that I had not told you the whole story when I said it should be filter, it should be activation. What else was missing? What's the 3rd ingredient that I must have? Some form of pooling. Now, which pooling you take completely depends on you. people like have rules of thumbs. Like for example, they have found empirically that for most images, if you don't have any prior information or prior belief, just go with max pool. Right? At one time, people used to go with average, but it all depends upon the data, right? And what would be most effective. So these are the three core ingredients that you need. And so today we say that every convolutional layer has this sequence. It has convolutional filter, filters, that followed by activation, followed by pooling to produce a feature map, right? A few channels of feature map. Now you realize that for each filter that, like at each layer, I get to choose how many filters I want to stick in, right? For that cat, I may start with 16 filters, let's say in the beginning. And so I will end up with 16 feature maps. And what will be the quality of these feature maps? They will be smaller than the original image. Would you agree? Right? So if I start with an image, which is 512 pixel by 512 pixel, then I'll get probably, assuming the kind of strides that I'm taking. Sorry, guys. This I'll take off this watch. It seems to be listening to me. Okay, so you take with 512 by 512 pixel, and then the next feature maps you're getting is less. But why would I want to create? Why would I like to use more features? Argue for it. Why would you like to apply lots of filters to it? Because each filter is discovering its own thing, isn't it? One may be discovering the edges, one may be discovering the horizontals, one may be discovering the verticals. That is, are we together? So the number of filters that you apply, and therefore the number of feature maps that you end up with after each layer, is a hyperparameter of the model. What is a hyperparameter? Hyperparameter is something that the machine cannot tell you the answer to. You have to know better. You have to have thought through, played with it, or just pull the rabbit out of your head. Like it says, okay, I believe 16 is a good one to start. And then try it out, see if it works. Are we together? And so with all these neural architectures, you'll realize that they are all infested with hyperparameters. There are lots of things that the machine cannot tell you the best of. Well, that's only half the story. Recently, there has been the emergence of a field called neural architecture search and Bayesian optimization, which actually very systematically and mathematically tries to find the best values for these. But we will leave that aside. In the first standard version, let us just assume that these are hyperparameters, and you get to decide. But the one thing that you don't get to decide is, what will these filters discover? Now, I told you that if a filter had values like this, -1, -1, -1, 8, -1, -1. I took this example, and I could have taken different example. What is this filter finding? Does anybody remember? Edges. This is an edge detector, right? It's an edge detector. But that was good to understand. In reality, because these numbers are just weights, what you really have in a filter is just W1, W2, W3, W4, W5, W6, W7, W8, W9. What will happen? How will these weights get learned? Through backpropagation. And so you don't know what the machine will decide as the optimal feature to discover in the image, isn't it? That's the beauty of it. So you better start with a large number of filters. Let's say you start with 16 filters. Let's at least extract 16 features from the image, isn't it? Are we together? You cannot get away with just one because that will be too little. Let's do that. Now what happens is, so the way the convnets work, and this is sort of what people found that works, is that they would start with a big image, let's say, with 3 channels, let's say, but let's say one big image. It would go, they would apply a certain number of filters, let's say 16 filters. They would end up with a smaller feature map of 16 now. So from 3 channels, you have gone to 16 channels. Right? Remember, each channel is one feature found in the image. Right? Then they would go to the next layer and it would be even smaller. Are we together? But the number of features they would find, now on each of these feature maps, they would find sub features. They would look for more information. And typically, they would go to, let me say, 32 features. Right? And then they would go, and then it would be, let's say, 64 features. And then finally, even smaller, and then finally small, and lots of them, 128 features. Do you see what's happening? A sort of funneling is taking place, right? Each layer is looking at a more global structure. Each subsequent layer is looking at a slightly more global, but globally it's finding a lot of features, right? It's finding a lot of things. And then what you do is, suppose, now the question is, this is all lovely, but how, for example, do I create a classifier, for example, to tell a cat apart from a truck? Right? Because these networks, ultimately, they need to do something practical. So let's take something practical. The simplest practical thing you can take off is an image classifier. Are we making sense? So what you do, what you do is, so you go through this layer. So I'll just mark this as like this. Huh? At the end of it, you end up with, let's say, 128 feature maps. Are we together? Then what you do is you do a flatten operation, which is sort of dumb, but you do it. You say that, hey, at the final layer, I have a softmax, right? This can tell, this is for cat, this is for dog, this is for truck, this is for horse, this is for house, this is for lake, right? This is for moon, or something like that, right? You realize that there's a softmax, and you need to light up one of them. But here I have all these feature maps which are not in the shape of this, isn't it? So what you do is, at the end of it, all of these feature maps, they together form a 3-dimensional matrix, a tensor. So you go through an operation called a flatten. So you will often see a picture like this, and a word here called flatten. Flatten is literally like that, scanning it from top to bottom and laying it out like this, all the values like this in a vertical. So how do you flatten a matrix? It's just literally as you flatten a matrix. Read row by row by row, right? And concatenate them. Yes, go ahead.
So my understanding is like in a single picture,
Yeah.
in the 28 by 28, it had a cat, dog in a single picture. Right? Finally, we split it into that. It is not separated. The single picture is split into.
Yeah, a single picture has become this, whatever was there in the single picture. Right? Yes.
So in the previous image, I
Yeah.
understand you're applying filters, it's becoming more feature rich. But is the image getting smaller?
Yeah, image is sitting there. The feature maps are getting smaller. You're not touching the image. You remember the image, that cat is still smiling out there. You're taking the cat. Cat was the input. At each level, you're creating more and more features, but each feature map, the grid is smaller grid.
Because you have multiple.
Because you're pooling, remember, because of the pooling operation. What does the pooling operation do? Look at this. If from 4 numbers I pick only one, what have I done to the size of the feature map? Reduced it, right? Exactly. So as you go down successive layers of this, you're reducing the size of the feature maps. Right? And why do you want to do that? Just to recap. Why do you want to do that? It is the zoom out operation. This is the way that helps you see a little less local structure, isn't it?
Yeah. But
So-
I mean, this has nothing to do with, you're saying, right, sometimes we take from a previous layer and put it in there.
No. Forget residuals. That's a completely different idea.
So
We
in this,
will-
in this example, like we are looking at the image which has only one object, which is like a cat.
No,
or
that
could be
it could be many things.
many things. So, but we are going to focus only on the cat. Is that what?
No,
we're
you're
trying to-
focusing on the entire image and trying to figure out what is it. Right? See, so okay, Ganges here is asking a question. What if you give it an image in which there is a bird sitting on top of a cat?
Yeah.
See, the point is that it depends upon how you frame the question. If you're giving it a picture and saying, what is it? Is it a cat or a dog or a horse? Then if you accidentally happen to give it a picture of a bird on a cat, what will happen is in your softmax layer, in the final layer, you will notice that the cat will get highly activated and the bird, let's say bird, will also get partly activated because it's seeing both. Isn't it? Remember, softmax is not that only one will light up. Softmax will give you different probabilities of each. And it will say, hey, I don't see much of a probability of it being a house, but I see significant probability of it being a cat and also probability of it being a bird, because I see bird features and cat features there.
Okay, so while going through that the series of feature reduction,
Yeah.
okay, we are sort of like a zooming in,
Zooming out.
Zooming out. It depends on like what's in the perspective of like seeing it, right? So because I want to focus more on a cat, or maybe
No,
like
why would you? The machine doesn't know what you want. Machine is saying, if you give me a picture, I will use my understanding to do hierarchical feature extraction and ultimately tell you what are the probabilities of any of the things that you wanted to classify it as. It will say the probability that it's a lake is low. Probability that it's a cat is reasonable. Probability that it's a bird is also reasonable.
so by zooming out, so I can see broader view.
Broader view. That's all it is. Right. So, any more
Asif,
questions?
Mani?
Yeah.
Asif sir, this is Mani.
Mani, go ahead.
Yeah, so I understand what zooming out does, but at some point you said uh, you will start seeing global view as you
That,
are. I
that is it.
didn't understand that part.
No, that is, you see, Mani, think about it like that. If all you could see is the eye of the cat, would you be able to tell it's a cat? I could equally argue it's a baby or it's a horse or it's a dog, isn't it?
Uh-huh.
At
Yeah.
what point do you determine that it's a cat? When you start seeing the cat's whiskers.
Okay.
So how does it do that? Hierarchy of features. Huh? It takes the eyes, it takes those circles. So basically what it says is, if I see circle, circle, mustache, mustache, right? Now what does it look to me like?
I see. So this is like using multiple feature maps and getting that information out, or it's just
Yes,
looking at
exactly.
one feature.
That is it.
Okay. So it's taking input from multiple feature maps and building it. Okay.
Exactly. It's taking.
Okay.
That's why it is. So think about it this way. In a very intuitive way, Mani, mathematically think of it. Suppose each of the feature maps were an input to a machine, right? One of them said eye, right? One of them said mustache, mustache, or whiskers. One of them said nose. And let's say one of them said roof, and one of them said water.
Mhm.
Now, these activations are zero, but these activations are high. Any simple machine, what would it come to the conclusion?
Some animal.
Yeah, it's an animal, right? That's the basic idea, that each feature, the subsequent layers are learning from the features of the previous layers.
Okay. So Asif sir, so when you said zoom out, it's like for each feature you will keep zooming out layer by layer. I mean, as you pass through the neural network, uh,
That's it.
basically getting essence out of that particular
Exactly.
feature, and then put all these features together, and then you get this global information and make a decision. That's what.
Absolutely. That's
Okay.
all
Okay.
that CNN. That is the core idea of a CNN.
Got it. Thank you.
So
Bhavin.
So,
hypothetically,
question.
picture had both a bird and a cat, as you're saying, and if both are of the same size in the picture, what kind of probability are we looking at?
Yeah. So the question Bhavin is asking, based on the neural architecture, a typical thing is he's saying, what if the cat and the bird are equally big? There's a hawk sitting on the back of a cat. Well, the hawk would probably try to lift the cat away. But okay, let's say you have a picture like that. What will happen is, and you can play this game and see it. you will notice that the probability of a hawk and see, these are the logits, right? These are the bulbs. You will see that the cat and the bird bulbs are lit up. Right? Those bulbs, those logits are.
So we can't predict the probability. It'll be 60-40, 70-30, 50-50.
Yeah, it will come up with some ratios, but based on the thing. But basically, they will both be lit up high. Yeah.
So what is the reason for flattening the feature maps?
I'll come to that. 1 second. Your question.
Quick question, like, so how does it know what kind of filters to apply to because that?
It learns through back propagation. That's the whole magic of neural networks. Like what filters to do by observing. See, imagine this is a child. It's looking at gazillions of images and it's saying, how do I look at it? It's somewhat like human beings. Did you know that human beings are born blind? Right? Our visual field, even though our eyes are functional, our brain has not learned to recognize objects.
Yeah, that's true.
Right? That recognition comes through the neural training. So human beings actually go through the same, in a way you can say, learning, we develop recognition filters of our own, feature extractors of our own, before we do it.
All of us see world a different way.
Yes, when we are born, we see without seeing it at all. Right? So something very similar happens here. Mani, I think you had a follow-up question. Would you like to ask?
Yeah, so, or,
okay.
So this is so you have 128 feature maps. Why not 1 million feature maps? And what's the correlation impact by increasing the quantity of feature maps?
See, the two aspects come in. The more feature maps that you create at each stage, the bigger the computation becomes, the more data you need to train it, the more, suppose at least people felt that they risk overfitting, though that one is now up for debate. Remember, the more feature maps you bring in, the filters you bring in, the more weights you bring in, the bigger your model becomes, the harder it gets to train, more data you need to train. So that's a consideration. 1 million feature maps, 1 million filters, for example, a 3x3 would mean 3 million things. Now, generally, you reach a point of diminishing returns very, very soon. And the reason for that is the visual domain, despite its complexity, when you look at it as a hierarchy of compositions of simpler shapes, actually, the visual domain is extraordinarily simple. It's just like, with 26 letters you can, in the English alphabet, you can get away composing an infinite variety of words and sentences and texts and poems. In the same way, in the visual field, the fundamental vocabulary is actually quite tiny. It's not as big. And usually you don't go to 1 million filters. In fact, people have studied that problem and they found that beyond a certain limit, you hit the point of diminishing returns very soon. In fact, it begins to get counterproductive.
Okay, thank you.
Anybody else had a question, guys? Vasanthi, I'm still holding on to your question. Anybody else? So, okay, I'll come to this question. Why do we need to flatten it? Remember, the last layer is a softmax. It's a flat layer. How do we feed the feature maps into that layer? Somewhere in the world, I have to say, oh, shucks, now this is all very good, but let me flatten it. Isn't it? Otherwise, I won't be able to, because there is no such thing as a 2-dimensional or a 3-dimensional or a k-dimensional softmax. Right?
So, say you had a horse and a dog.
Yes.
Similar features.
Yeah.
And if you flatten it,
yeah,
I imagine the features are like all over the place.
They are not, because the flattening is a very precise operation. See, if you take this, you're scanning it like this, right? Line by line, and you're laying it out like this. So you can convince yourself that they will be different. Also, you have to remember that by the time you reach these many features, those are very abstract things, right? Those features are no more your nose, your edges and eyebrows. Those features, and and that is why I asked you guys to please play with that CNN explainer. You would have seen that as you go down the CNNs, in the beginning you can recognize. Remember, you could recognize the edge of the Let's go back and see it. Look here. Look at this. The first convolution is doing this, right? And when it is doing this, you see this picture here. This filter is producing what? A pretty good image of a cup, the edges of a cup, right? And if you look at this very carefully, this filter, kernel weights, can you tell from this kernel weights what it is doing? Look carefully.
Asif, there was a question yesterday, like why were there 3 pictures instead of one on the left?
Oh, because of the red, green, blue RGB channels, red, green, and blue. Right? The way modern cameras take picture, they take it in 3 different colors. They take a red picture, they take a blue picture, and they take a green picture. They separate out the wavelengths.
The M is like we given the name. For example, one means in a way like.
Let me hold that thought, guys. I'll come to that question. I know what you're coming to. So, guys, please pay attention to this fact. Do you see how crisp these pictures are? In the initial layers, how crisp it is. Right? It's very crisp. What happens to pictures here? In this picture itself, just 3 layers deep. By the way, 3 layers is too little. Do you see that the cup has become into a much more vague representation of a cup? In 3 layers, it has become this, right? And can you see from this, right? This cup that, and obviously this is a oversimplification of the situation. If you look at, maybe I'll try it with something else. Let me see what it does. Yeah, notice that this ball, all the features, all the local features are lost. In the last layer, do you see these dots on this 2 dots and this where my mouse is? That line on the ball are more or less lost. Can you tell it, guys, when you look at the rightmost feature layer after max pooling, can you see those dots? No. What has it done? It has created abstract art out of it. Right? It has come because it is from it deriving things that to you means nothing, but to it means a lot. Right? So, for example, when it is coming out with something like this, and it says, yeah, this is really useful information. You go like, what? But it needs this information. It needs the information that there's something spherical, right? Do you see that? There's something spherical here that is there. And so that is the way these machines reason. They come out with features that you and I wouldn't come out with. These machines do their own thinking. Now comes the interesting thing. If I'm going to flatten it.
Yeah.
You've made the comment multiple times that we don't fully understand why it does what it does. Is what you just said an example of that in a sense? Because as it gets bigger and more complex, it abstracts out further and further. And when you look at that, you're like, wait a minute, what is that trying to do? We really don't fully understand quite yet.
But that is right. It turns out that convolutional network that I'm teaching you, the first neural architecture, non-trivial neural architecture, today we actually consider it to be reasonably interpretable. Not fully, but reasonably. If you think long and hard, and if you develop a lot of intuition or experience into it, like for example, I told you what it was looking for, why it was such, blank thing. So people have through experience gotten some insight into how the machine is reasoning about it, right? So CNNs are relatively benign, I would say, interpretable. And the other thing is, as we will learn, it is much easier to impose an interpretability machine on top of it. For example, you can create things called activation maps. That's a big topic called interpretability in complex machine learning algorithms. You can impose interpretability to see why did it make a decision. So what would happen is, if you look at a picture of a cat and you ask, why was that a cat? What made you think it's a cat? What it will do is, it will go and say, I paid more attention to this. I paid more attention to this part than to other parts. This was a giveaway, right? And maybe I paid some more attention to these two things.
So,
These were giveaways.
so Asif, so this is another form of feature engineering, right?
It is, and that's a good observation, Prashant. But you said, I'll repeat for everyone, you said it's a form of feature engineering. So if you go back and look at the literature and the conversations that were happening a decade ago, people just stood up and said, wow, in traditional machine learning, we had to do a lot of feature engineering by hand. You had to be clever. You had to be an experienced machine learning engineer, machine learning expert to be able to think what features make sense. Think of it, a biologist. When they know, for example, if you, let's take something very trivial. You're a real estate agent. You look at a house instinctively, you said, doesn't matter how long it is, how broad it is, how many floors it has. Tell me what's the square footage. And that's how I will compare the price of this house to its neighboring house in the same neighborhood, isn't it? Right? So you just said, I know what feature it is, what feature matters. That is feature engineering. Now, what these machines are capable of, people realize in deep learning is the word that Jeffrey Hinton used is representation learning. And I was going to come to that, but since you mentioned that, let me use that. Present, I must be writing it up, P-R-E-S-E-N-T, big word, representation learning. Representation is what is the best in representation, or you can think of it as feature engineering, but a more formal term is representation learning. What it is doing is the machine is looking at the input data and coming to its own conclusion on what is the best way to represent these features so that I can best do the task of, let's say, classification. Are we together? So we use the word representation learning. In fact, in older literature, in fact, if you go back to the book Deep Learning by Ian Goodfellow, Yoshua Benji, and so forth, you will notice that the book starts out, that book is now a little bit dated. I believe it's 2016. Gosh, in our field, things move so fast, right? It is written by the great luminaries. And I believe, if I recall it right, I read it years ago now. It's been a few years since I last read it. It puts quite a bit of emphasis that deep neural networks are representation learning machines. They automatically learn features. All right, guys, any questions? I think you had a question.
Yeah, so when the feature maps are all with before the 28 by 28 pixels of the image, where the names are there. Okay, cat, this is the cat, this is the sun, this is the thing. How do we?
You don't do that. All that the machine produces. So remember, stay with me in the journey. Once you flatten the image, you can theoretically feed it into a softmax, isn't it? But see, your softmax vocabulary, you determine what size of vocabulary or how many classes there are. You may be looking across 1 million objects, let's say. Or let me just take a smaller number, 1,000 objects, and saying which of these 1,000 objects it is. That's a classifier. Remember, you have to tell which of the possibilities are you looking at. So now what happens is you realize that this may belong to a dimensional space D, which is different from which may be different from 1,000. Isn't it? Guys, does this make sense? You create features, you flatten the features, you'll end up with a vector in some D-dimensional space that D may not match how the classifier object that you're looking at. Common sense? Right? And so what do you need in between? You need some, in the very minimum, you need a transformation matrix to align the dimensions, right? To project it into that number of dimensions before you feed it into the softmax. But while you are at it, why just do a linear transform? This is a great opportunity to do also what? Activation. And while you are at it, why just one layer of activation? Why one layer of? So now you're putting it, the moment you do this plus activation, what does it become? It becomes one layer of feed forward network, right? One feed forward layer. But why just one? While you are at it, let's take a few more. right? So this is the way people do this game. They may stick in a few more layers here. So your architecture therefore becomes, in the general case, you have an image that goes through, let's say, these many layers of convolution, producing a lot of feature maps, which you flatten out, typically flatten out. There's a flatten operation, followed by a few your standard, a few layers, followed by, let's say, softmax. Are we together? For classification, you can have a softmax.
But what is, first of all, won't that add compute? And secondly, what is the benefit?
What's the benefit of that? So won't they add compute? It does add compute. So therefore, don't go wild on it. Just keep it to a few. What people realized is that after flattening, you have to do a matrix multiplication projection anyway. You might as well throw in an activation. It's cheap, relatively. And after that, don't stick in too many layers, right? Keep it to 1 to 3 layers and then produce your output. But so how many layers are good and why should you stick in a few? It all boils down finally to just empirical. Nobody knows why it's a good idea, right? The mathematics has not yet been worked out. Empirically, we know it's a really good idea to do it, right? Things work out much better if you do that.
From that point onwards, there is nothing CNN. This is regular.
It's just
feed
MLP, multi-layer. So people say
Yeah,
these
but-
two words people use interchangeably: feed forward,
forward or MLP.
layers, or multi-layer perceptrons, uh, or linear layers. These are all synonyms, guys. Different guys will, or dense layers. So whenever you see these 4 words, they are referring to the same thing. Are we together? You stick that in and then you are done. Right? So what I will do is, this is a good point to break.
But one question I have, okay, during that, like the CNN up to the filter map.
Yeah.
Okay, that during the training phase,
Yeah.
even we have this like MLP or only.
Yeah, of course, this is the whole. So your entire architecture is this. So this is your complete, you would say, CNN. This is your full CNN. And so what would you do? Let's go look at it. Let's take a real world example, since you asked this question. Now I will represent the entire CNN with its softmax as a box. CNN. And I'll deliberately put the softmax on the side.
I think Asif's picture just froze.
Yeah, it looks like that because
Okay.
I was about to ask if anyone else can. He's frozen as well.
Yeah, looks like some network issue from Asif's end.
Yeah, anyone in support vectors, just let him know, please.
Well, I guess class got out early today.
He must be trying. Actually, he wanted a break also.
Yeah.
Can we take a 5 minutes break? I will let him know.
Yeah, that makes sense. Go ahead.
Sure. Oh, he said 10 minutes break right now. Person.
It looks like someone
Okay.
in class is standing up there, and so I'm guessing they are on a break.
Sure, let's take a break. I'll let him
I'll
know.
just give him a call and let him know.
Yeah, sure. 10 minutes, 9:20 will meet India time.
Sounds good.
Okay. No.
Then we like applying this. So that if you give any new image, then you start with
There's the test phase. So then you basically testing it. Then there is some problems. It's like
All right, guys, let's get ready. All right, folks, can you hear me? Those of you who are remote?
Yes, Asif.
Yes, we can.
All right, we can continue. So we have reached the stage at which we now know the full architecture of a basic CNN. Do we agree, guys?
Yeah.
Right. So now I'm going to draw the CNN in two pieces. Everything here and a softmax here. Right? Think of it like this. You show it a picture of an image, a cat, and then it makes a probability cat given input. So x is equal to this probability of a cat given x and all the weights and biases that are here. Let me just write it as theta, the parameters, right? Parameters. Ultimately, at the end of it, this big architecture is a box of parameters laid out properly, isn't it? And so this would be bigger than, say, probability of a truck given x and theta. Would you agree?
Yeah.
That's the point, right? So it will light up the most. Go ahead.
Parameters model first.
Say that again louder.
The parameters.
Weights, all the weights and biases, all the weights and biases. Yeah. So whenever I say theta, theta is a collection of weights and biases. Are we together?
Yeah.
Is a set of all the weights. So CNN is an interesting architecture, but at the end of it, it's a box of weights and biases. Right? And this box of weights and biases, what happens is, so very much like, how do you train this box? In the beginning, you give it a cat and it will produce a random probability, right? It may, for example, say probability of cat is only x theta is only 0.1, right? And it might go and say probability of a house x theta, let's say it may come up to 0.7, for example. So what happens? This is wrong. You need to push this up. How will you push this up? Once again, just to recap our basic machine learning, you will create a loss function that penalizes for this number being low. What is that loss function? Negative log probability, right? Negative log probability of a cat given x theta. And so as this, you would do the standard training loop. You will take the gradient. From the gradients, you would backprop. Then you would take the step that each of the parameters, whether it's a weight or a bias, it would go to previous value of weight or bias minus alpha gradient. Actually, let me just use the word theta, some particular theta, or let me just use the word weight. Assume biases also, of course, right? Minus, right? This is your basic learning step. Are we together? You can train it. Now what happens with, so guys, at this moment, I hope you understand what convolutional neural nets are. They are a dominant architecture. Believe me, they are the simplest architecture. After that, things will get more complicated. Right? The things that have come recently are a little bit more involved, right? But it is core. you use it extensively. What you do is you add more things quite often to this kind of thinking. Now, one question that comes up is when you, with this CNN architectures, people began to see that there was the AlexNet. Actually, why don't we visit some of the core architectures and show you how they look like, right? That should be instructive before I close the chat. Oh, sorry. It disappeared. Before I close it, here, if you notice, collection of CNN structures. By the way, just to give you an idea of how complicated it can be, I put here one of the architectures that is pretty deep, and it tries to understand how the machine sees internally. How is the machine looking at the image? So can you tell that you start with the image like this? Look at the left and look at how the machine is thinking about it. Quite interesting, isn't it? Right? The features that it saw in the image are quite interesting. Right? I encourage you to go and think about or look at these visualizations, ponder over it and see what it means to you. I won't go more into that, but I'll leave it to you to do that. Now, let's go look at some of the architectures. When you look at the core architectures, let's go and start with the simplest, 1998, Likhon. Oh, no, now his password protected, but we can go. Likhon architecture. Okay, guys, now look at this and tell me that you can understand what it is. You have an input, let's say the letter A. What are all these? Feature maps produced through a process of convolution. What is this subsampling that he's talking about? It is pooling. Then more convolutions. At the end of it, what do you end up with? Lots of features. Second layer of convolution. Subsampling. You get even more features. Are we together? So in today's time, it looks almost primitive. Just two convolution layers followed by, what is this? What is this thing? Flatten. Followed by some fully connected layers, right? And then you have an output 1 to 10. Why? Because you're talking about 10 digits or something like that. Output, right? But observe this thing. You started by 32 by 32 images. You end up with six features at 28 by 28 because they didn't use padding. So you lost some. Then you did subsampling. It became 6 at 14 by 14. So you notice that half. Then you ended up with feature maps, 16 of the feature maps in the next convolution. So you notice that you went from just 1 to 6 to 16, right? And then it stops. After that, it just becomes feed-forward layers, right? So very simple architecture, and yet it could do pretty good handwriting recognition. Yeah. Let's go and look at AlexNet, which won the prize after that.
Asif, quick question. So
yes.
Yeah, in the previous one, there is 6 feet, like 6 into 28 into 28, right? So
Yeah.
that 6 layers are from each feature map. Sorry, each
filter, 6 filter. Yeah, 6 filters.
Okay.
6 filters were applied. You can always tell how many filters were applied by looking at how many feature maps are produced, because each filter produces one feature map. Right? So that is that. And if you look at the code, and I encourage you to look at the code, guys. If you look at this code now, you see how simple the code looks. Let's read this code. What are we doing? First is a convolution, right? 6 filters. Can you tell the 6 filters here? Right. What is the filter size? 5 by 5. It used 5 by 5 filters, right? The 3 is the 3 channels, RGB channels. Then you have 6 goes in now, and you produce 16 filters, right? 16 filters. And then it produces, and then finally you linearize it. You notice it flattening? You flatten it, flatten, and linear, linear, linear. And see, let's look at this. The input comes, first you give it to the convolution, and then you activate it, and then you pull it. So this together, line 15 and 16, make up one convolutional layer. In modern language, you'd say one convolution layer. 17 and 18 make the second convolutional layer, isn't it? What in the world is this thing? When it is saying make it into one single flattening, followed by feed forward, 2 layers of feed forward, third layer of feed forward produces the output, basically, right? So this is it. This is it. You see how simple it is in code today? Now, let's go and look at AlexNet.
Can I ask a question?
Yeah.
So if you go to that code.
If I go to the code, yes, go ahead.
So the thing is, in the linear layers, there's matrix multiplication. So the output 120 goes to the input 120.
Yeah.
And that part I guess. But for the convolutional layers, it ends at 5 and then it goes to.
No, because convolutions, the parameters are not the matrix sizes. Okay. It is the filters. How many features you take, how many input channels, output channels.
Okay.
Input, output channels.
The output will be 6 by 16 into 5.
Yeah, look at this.
That is why it is input.
Look at this line, for example. What it is saying is, I will get 6 channels of information, okay, and I will apply 16 filters to produce 16 channels of output. The size of each filter is 5 by 5.
Okay. I see. Okay.
Right? That's a way to interpret.
What is the 120, the linear?
Okay, so finally what you do is you say that I have a linear layer, which is the flattening thing. What I do is, it is this. Why 16 times 5 by 5? Because literally that's what it is, right? And then you flatten it out, but that is your first layer. But output, after flattening, the first layer therefore needs so many elements, but how many neurons will the layer itself have? 120. Next neuron has 84, next neuron has 10. Right? Remember, read if you want to find how many neurons are in a feed-forward layer, always look at the output part, the second argument. Right? That's that. All right, are we any more questions, guys, in this code? I hope this code now looks dead obvious. Does it? And what kind of pooling have they used?
Max pooling.
Max pooling. Right? Why did they use max pooling? Yeah, that is it. Yeah. So max pooling helps here. So
is it really is the rule of thumb to kind of go for activation, or
rule of thumb? No, without activation, you don't have a network.
No. Which activation function to use?
Oh, which ReLU? Yeah, generally ReLU or some variant of ReLU is the best. Simply because it works. Actually, these days for transformers, GILU is the best. If you're doing CNN, some variant of basic ReLU is fast because you want to do it fast. Right? So you do it pretty fast. Okay, let's look at now AlexNet. Oh, what do we see? It's a little bit more complicated. Do you see that, guys? Huh? It's a little bit more complicated, but it is pretty much the same architecture, except that it has you will see its diagram. This is the diagram. Let's look at the code because the code makes things much more clear. There we go. So guys, do you notice anything tremendously different here? Classifiers is just the feed forwards at the very end. That is easy, right? Because they use one dropout also. What is dropout? Dropout means some of the neurons just ignore it, ignore the output. Some percentage of neurons just ignore the output. It comes under a topic called regularization of a network. Now, there's a bit of a history to dropout, guys. when dropouts were discovered in the 10 years ago, people thought they had a great way to do regularization. I haven't covered dropout. I haven't explained to you dropout. For a reason, because I have to select which topics to teach. Think of it as a regularization technique that deliberately ignores some of the outputs and moves forward. We thought that dropout is a really good idea and you must do it. It was all the rage to use dropout. But over time, we now are not so sure anymore. Why? Because we have come up with better techniques that has sort of muted down the relevance of dropouts these days, right? We don't take it that important. Right? Some may even argue that we can do without dropout if we use some other ideas in the mix. So, well, this is AlexNet 2014 or 2012. So you can see 2012, I believe. The dropout had just come out. It was a good idea, but ignore the dropout completely. Wherever you see dropout, imagine you are not seeing that line. Rest of it, guys, do you see that this looks very, very familiar? Do all these things look familiar compared to what I taught you? Right? That's that. Then we go, this is your AlexNet, very successful. This AlexNet was considered in computer vision.
This code, they use the ReLU on the convolutional layer as well.
ReLU.
But not on the far.
No.
But for the
why not?
The other code, we didn't see that one.
No, it was also using ReLU. Oh, ReLU didn't exist at that time. Let me just go back and see. What you're talking about is this guy, right?
Yeah.
Today, when we implement it, linear, you see the ReLU here.
Yeah,
Here is the ReLU.
we do that in the forward.
Yeah.
But not on the.
Oh, it is just a different way of writing the same code. You could write the code either way.
Okay.
ReLU has been a good idea for a while. Linet today, when we implement, you should implement it with ReLU. Though some of the earliest implementations that people are doing with the architecture, they were using TANH. But now ReLU is the way to go. So,
I was thinking about this training process. So once you have this model, especially for this image data, you gotta give some data and some labeling to it, right? So what does that process look like?
Oh, that is a whole bunch of human beings sitting down and putting in a table. This image, name is this. This is the label. So labeling was a human process.
Even today, that's how it is now.
Today we try to cheat a little bit. We try to make the machines label the data as far as possible. Right? But it is a mix of machine and humans, but humans are always there. Labeling is a very expensive process. So there are companies, entire companies which make their livelihood by simply labeling data for. Yeah. And in fact, one of the interesting things that has happened is one guy in India. I didn't turn this out. One guy in India decided that, see, lots of unemployment in India. People have basic education. Lots of label data needed for AI. Win-win on both sides. And he started a company in which he pretty much employs a lot of people in India to do the data labeling. He has a data labeling platform. And a lot of people use those services.
Kriya.net, I guess.
What's that?
Kriya.net. Right?
Kriya.net. Yeah, probably. I don't remember the name of the company.
Yes, so it's basically shared the revenue to the Kriya labelers.
So I mean, just going back to that example we were showing before the break of that playground with the cups and all that, right?
Yeah.
That was a result of the model that was trained to recognize a cup based on that image, right? Because it could
that is right.
Coffee.
That is right.
Somebody could have labeled it as coffee and could have predicted coffee, but in this case it was trained for cup.
Absolutely. You have to give it label data to get it. So guys, the next evolution is a VGGNet. VGGNet came from Microsoft. Very deep convolutional network for large scale images. Let's see how deep people in those days used to consider very deep. Right? Well, not that deep, like 11 weight layers and so on and so forth. Let's look at the architecture of this. Look at this. Today, you wouldn't consider it very deep, VGG, right? But it was quite successful. Then came models like, after VGG came GoogleNet, or Google's variant on DeepNet. And look at the heading of the paper, Going Deep with Convolutions. It's a very interesting paper. I would encourage you to go read this paper. Oh, this guy cannot be used, so the website itself has gone away. It's part of the history of it. Let's look at the visualization of it. Wow. Guys, does it look deep enough? Right. So it's getting deeper, and you have inception layers, etc., etc. I won't go into the inception idea at this particular moment. And then you have inception V3. This one is worth looking into, ResNet. Do you notice that in ResNet, you have this short circuit paths? Residual. These are the residual short circuits. And then you have squeeze nets. I will stop at one of them. Let me stop at inception. Inception, if you look at it, by now it's getting complicated. But at the end of the day, it is just rewiring those pieces in different ways. Are we understanding it? The basic building blocks that I explained to you, it is just rewiring it and saying, you know what, if you rewire it this way, you'll get this benefit. If you rewire it that way, you'll get that benefit. So that's the story of CNNs. They have been widely successful. You can use it to classify. CNNs also gave birth to the concept of transfer learning. So transfer learning is something I'll talk about now. And so I brought up this picture. This picture. So suppose you trained a network on 1,000 images or 1,000 types, 1,000 classes, right? Or 1 million classes and so forth, ImageNet and so forth. Give me a moment. I think I'll sit down now.
So if your camera's, you're falling off to the right on your camera view.
And is that better?
Yeah, we can see your mustache now.
All right. So one of the things that people realize already, two things happened. This companies in hardware that saw the opportunity, the big thing that AI was becoming, began to take off. Right? NVIDIA in particular caught on to this opportunity early. They were the guys making gaming video cards. They were, at that moment, I remember that if I had to buy a good video card to drive Linux, it was either NVIDIA or there was a company called, which AMD acquired, called ATT or something like that. Does anyone remember? Radeon. Then it got converted, renamed to Radeon or something like that. It's a Canadian company, right? Yes, it was a Canadian company that they acquired. So you would get a graphic card from there. Graphic cards were used also for like the design crowd, movie making crowd, and the design crowd, etc., were using some of it. But there was a new market that suddenly people saw the potential of, and NVIDIA, to its credit, saw the potential of, and they started investing on optimizing their hardware for the sort of matrix multiplication that would be needed to drive CNNs. A great decision in hindsight, and that one decision is why I'm told that today its net worth or market cap exceeds the GDP of countries. In fact, 1 year GDP of Canada is smaller than the total net worth of NVIDIA. is that huge, apparently. So it's very interesting how ideas lead to world changes, actually, in many ways. But now I'll talk a little bit about this whole concept of transfer learning, and then I will use the time. Oh, it's already 9:30. We'll use the time to at least introduce a new concept that I'll talk about the next time. See, what happened is people would take a lot of energy to train a model. And let's say that the purpose of the model is to tell between 1,000 classes, 1,000 classes. Now, look at the problem that I gave you guys. Pepper tree versus weeping willow. Right? So suppose you have to tell apart between just two things. A tree that goes like this and a tree that is like this. Right? Weeping willow and pepper tree, two trees very popular in California. And I ask you to tell them apart. Now, this general purpose model may be good at many things, and it may do reasonably well telling this apart. But what you can do is you can further train it to be better. Now, to train these models used to take a lot of compute power that most of us didn't have access to. And so, to the credit of these researchers and these companies that were training these models, they started releasing these models, call them pre-trained models. So all of these, your ResNet, AlexNet, VGG, etc., these are pre-trained models. You can download them, and then you can further tune them on your problem. In fact, that is your homework now. Take one of these CNN models, fine-tune them to distinguish between pepper tree and the weeping willow. Are you together? And see what it leads to. There was also a further discovery. So now this is about CNNs, guys. I'll stop with CNN. CNN can solve a lot of problems. It turns out that you can use CNNs for words also. If you think of words as one-dimensional images or one-dimensional context, feature sets, you can apply it to, of course, sound. You can apply it to video. And CNNs have been a dominant, and at the end of the day, one of the simplest architectures, neural architectures that you can think of. It's a building block. So there are two building blocks that you have learned now, the feed-forward network and the CNN, isn't it? Now, what can we do with that? What I would like to do at this particular moment is, guys, can I go for another 45 minutes today? I see a lot of enthusiastic yes. Yes. All right. So I'm about to end CNN. If anybody has a question or a comment, let me know. Guys, I hope you got, 2 weeks. CNNs used to be an entire course in a decade ago. We have covered CNN in 2 weeks because we have a lot to cover. Was this introduction useful? Like, did you get a sense of what CNNs are?
Yeah. Very good.
Thank you.
I think one question I had about in the context of multimodal, right? So now you're saying that the same model can do the text as well as image interpretation. I know traditionally you said transformer is the one that you use for the text interpretation, and then CNN you use for this. But are these new models doing both?
All of them simultaneously, and we'll come to that. Yeah.
Ashok,
Transformers are a game changer. We'll come to that later. Go ahead, Madhu.
yeah, there was a question in TA session yesterday about dropout, so I'm assuming you would cover that a little bit in the next session or something.
Yeah, I can give a basic idea of dropout, guys. What happens is that to suppose a machine is producing in a given layer, lot of firings, right? Each of these neurons are firings. What you deliberately do is that to the next layer, you go and zero out some of those. Randomly, you go and zero out, let's say 20% of the firings. Irrespective of whatever they produced, you just set it to zero. Why do you do that? You basically want the machine not to overfit to the information coming out from certain neurons, right? So you give other neurons a chance to also pick up, pull the weight. That used to be the concept of dropout. See, the intuitive argument sort of makes sense. There's a paper about it and so on and so forth. Today, when we look back at what it, so I can tell you what it does to the loss landscape. It creates spikes, like, porcupine has spikes on its body. So it turns out that when you look at the loss landscape, and why don't we look at it? But then we are cutting out on the time. But okay, that's all right. This is important. Let's look at the. If you go back to your course, you notice that I've given you a link to the loss landscapes. Loss function. Somewhere in here is a loss function. Gradient descent, PyTorch, backpropagation, loss functions here. Day 5. A survey. Oh, I didn't put the link to the loss landscape,
No,
did I?
it is there. I think it's in the day 2. I suppose.
Day 2. Okay. Day 2. Yeah, we're still going back.
Maybe day 1. Or maybe. Saw that.
Yes, here it is. Loss landscape visualization. If you go to loss landscape visualization, and if you look at the gallery of things, somewhere, no, not this, videos. Yeah, do you see the spikes here, guys? Dropout. So watch this video, what dropout does. I'll post this video. Do you see this dropout? What do you notice in the, let me make it full screen. Is the sound being transmitted?
Yes.
So this is the machine is learning. So you can see that as it is learning, the surface is changing. But do you see the spiky things here? This pointy spikes coming out. This is because of the dropout. This is what dropout does to the loss landscape. Makes it very spiky. Right? Now, the question was, what's the use of it? We thought it was for regularizing. And actually, this visualization was one of the things that made people think, really? Was it really supposed to do? Do we really want spiky loss landscapes? Right? Because it seems to be adding a kind of structure we didn't anticipate, isn't it? So today, we do use with dropout as one of the techniques, but we don't overemphasize it that much. Right? It's just part of the story. But anyway, I'll cover it more properly, all the regularization techniques and how to compare and contrast them with each other. See, guys, it's such a big topic that typically, when there was a time 2-3 years ago when some of the new architectures had not come, we used to give 2 weeks to it. Right? But now we don't have time. I'll do it separately, but not in the regular course itself. All right. Any more questions, guys, before I stop the CNN?
So, I think in the beginning of the class, you said today we're going to talk about autoencoders.
Yes, and I want to move to that topic. That's why I'm asking you. And thank you for agreeing to be here an extra hour. No, I have not. So, well, anyway, jokes apart, it's going to be 9:30, guys. So it's your choice. We can cover autoencoders next time and just take question answers on CNNs now. Is that what you would like?
Better to digest whatever we learned.
Okay. You can digest that. All right. Then all right. I'll stop with CNNs and I'll take questions. Any more questions? See, guys, I'm getting the feeling you guys haven't done a lot of self-study. You guys are all professionals. You're living busy lives. And obviously, nowadays, engineers are having to do the work of many more engineers, as employers have found to their delight that they can lay off people and still expect the remaining ones to do all the work. Right?
So you said like that the homework's going to be RSET and AlexNet. So what do you suppose to that?
Yeah, I'll write the homework down. Basically, guys, okay, let me talk about the homework. What I expect you to do is step 1, and I'll write it down. Download a lot of pictures of weeping willows. Do we know what this tree is like, guys?
Now it's all springtime, it's just still coming up.
Weeping willow will be there in every garden.
Every season. Yes, exactly. Weeping willows and pepper trees. Pepper trees. Now, those of you who are on the East Coast, I don't know if pepper trees exist there or not. Can somebody confirm? If they don't, I know weeping willows exist. Pepper trees, I don't know.
No, we don't. Weeping willow, yes, we do.
Okay, replace it with whatever exists on the East Coast. Some tree, some common tree, but pick something that is a little bit similar to weeping willow, and then write a classifier. Train a CNN classifier on it. Right. Start with a pre-trained model. Pick your pre-trained model. You can pick BGG, ResNet 50, whatever. Pick your little CNN and train on this. Right? Download a lot of pictures. So by pictures, I mean 100 each. And do this, guys. Can I expect you to do this? This is a simple exercise. Now, for those of you who are willing to go the extra mile, don't download, take original pictures. Take original pictures of this. And by the way, I don't know how many of you are nature lovers. If you do go hiking, or if you do you have a beautiful arboretum or something in your neighborhood, trees. It's a pleasure, actually. Especially these days, everybody has access to a really good camera in their phone. So you can take pictures quickly. Oh yeah, so what you will do is you'll create a data set, and this is where you'll learn, use PyTorch. Use PyTorch to do this. Use PyTorch to do this, and bonus, redo it with Hugging Face, but not needed actually. Actually, let me take Hugging Face out of this because it makes it too simple. Just use PyTorch to do this. Guys, this thing, if you especially download the images, the entire exercise will take you a couple of hours. Can I expect you to do this, guys, this week? Please do this.
Can you explain how?
Asif, roughly how many images should we be training this on? Like, any idea?
100.
100, okay.
Can you explain how to select the model and
No, that's what I'm saying. As you go and look at pre-trained models, the good ones to pick are VGG, ResNet, etc.
download that?
Yeah, you'll just download that. Start with a pre-trained model. You download.
Those are like on the Hugging Face or something.
Go to PyTorch. PyTorch will give you a way to download these models. Right? By the way, guys, this example is so basic. If you just go and read the PyTorch Torch Vision documentation, which I have linked to in the course portal, you will practically see the whole solution there, right? So it is not a hard exercise. It is just meant to make you familiar with this. So if you go here, let's go here. CNN, convolutional networks. I've given you all of the resources, guys. Do you see PyTorch Vision? Guys, go to PyTorch Vision. What do you notice? Here it is. And there are examples and tutorials. Let's go and get started with examples and tutorials. Right? What do you see? You will see that download all examples of, well, I shouldn't say practically all the solutions you will practically see here. Now, if you go to the tutorials, right, you will notice that for CNN, there are images and videos, torch vision, object detection, computer vision tutorial, transfer learning. So this is it. Fine tune the ConvNet, right? And when you look at it, you'll practically see the whole solution in front of you. I will be walking through the solution later on, but it would be far better if you tried it on your own, read the tutorial and did it. Right. So look at this, guys. Does this code, for example, make sense to you? Let's look at this code, guys. What does the for every epoch stand for? Epoch of the data. For each phase of training and eval, that's okay. For each iterate over data, what is this? Inputs, labels, what are we doing here? Getting a mini batch? Mini batch. What are we doing? To device, this is pushing it onto the GPU. Optimizer, this is just resetting it. What are we doing? The forward journey. Forward journey is what? Model, you give it the input, it produces the output. Outputs, from there you get the predictions. Then you can create the loss using the loss function. Then you do the backwards part, backwards training and so forth. So guys, try to write your own code. This code is unnecessarily complicated. For example, if phase is training, do this, etc., etc. In your case, write a much simpler loop. The way I gave you the loop in the original code, PyTorch code. Use that.
Asif, in that for loop there, inputs and labels, that's where the picture and the label for pepper
Absolutely.
tree
Picture and label comes in. And how do you feed it the pictures and the label? This is the data part of it. What you do is, and now let me talk a little bit about the data. See, guys, there is a library called the PIL library, right? Python image library. Now, this is what this uses, but now this project has been forked, and there is a better library called Pillow. I would suggest use Pillow, but you can use PIL itself. Right? It helps you load the images. Now, when you take the image, one of the things you want to do is, there's a bit of a data normalization you want to do. Suppose you get a cat. Your image may come in different sizes, but your algorithm will take image of a particular size. So what do? You crop it to a certain size, right? You may do some horizontal flips. Why? Cat looking left, cat looking right shouldn't matter, right? And then you convert it to tensor, that's all right. Then normalize it. Why would you normalize the data? Oh, where did this magic numbers 0.485, 0.51, etc. come from? What they do is they are saying that you need to normalize the data. What does normalization mean, guys? Do you remember? Normalization means what? Suppose I give you a bunch of numbers. Suppose I give you a number A, B, let me just say A1, A2, A, M. What does normalization mean?
Making the sum fall within a range.
Yeah. What you do is normalization, there are many ways of doing it, but the basic normalization that you do is you can see Zi, so this is AI, is AI minus mu over sigma. Right? This is a Gaussian normalization. And why do you normalize? For many reasons. A practical reason is in the neural network, when you do matrix multiplication, you don't want to multiply huge numbers. You want to multiply small numbers. But a more intuitive explanation is, you see, guys, I may choose to weigh an elephant in tons, 1 ton, 2 ton, right? So an elephant may weigh a couple of tons. You may choose to weigh an elephant in grams, right? So now you would come up with 1 million grams for this elephant, 2 million grams for that elephant, isn't it? So based on the units we use, we will, for the same elephant, we'll come up with very different numbers, isn't it? But one thing is for sure, that if these numbers, they're unit dependent, but you would agree that the average elephant weight should be, like, the statistic should be still, even though it is unit dependent, we should be able to find the statistic. And relative to that, we should be able to tell greater than average, less than average. Does that make sense? Isn't it? And so, irrespective of the unit, I should be able to tell AI minus mu. If it is greater than 0, you're heavier than average. If it is less than 0, you're lighter than average. And then the other thing is, those numbers have a spread, certain variation, right? What you do is, if you divide it by the standard deviation, then all of your weights, irrespective of your units, they will be centered around 0, the average centered around mu, right? This quantity Zi is called Z scoring or normalization, Gaussian normalization. And you can do this little experiment in your mind and see that it will always come up with 0 centered, and most of the values will be between -3 and 3, right? +3. In fact, most values will be between -2 and 2. And these would be the outliers, very, very few outliers. Are we together? And so the reason you normalize mathematically, the reason is because you notice that, suppose it is in it is in grams. When I subtract it, so I may be subtracting, this is in grams, this is also in grams. So the unit of A minus mu would be grams, right? But then the standard deviation is also in grams. When I divide it by standard deviation, what does it become? Dimensionless. So it becomes invariant of the unit. It doesn't matter whether the unit was grams, kilograms, or ton.
So Asif, what is mu? Mu is the average of all the weights.
Mu is average.
Okay.
Sigma is standard deviation. Average. Does this make sense, guys? That is why it's always good. In a way, this is a more natural unit to look at an elephant, right? So, for example, if an elephant has a Z of 1, what does it mean? It is 1 standard deviation above the average. Does that make sense, guys? Rather heavy. If it is 2, if Z is 2, well, it probably looks like me, quite heavy. Right? And so forth. Right? So that's what a normalization means. And there are many ways to normalize, but this is the most common. In machine learning, the normal Gaussian normal is the most common. So what do you need? You need the mu and the sigmas, right? Vectors in 3 dimensions. So you do give that RGB channel, right? Remember, you have the red, green, blue channel. So you will have a mu for red, a mu for green, and so forth. So that's what that is.
Where did the number came from, the normalized?
Oh, just looking at the entire data set and taking the averages, finding the mu and sigma for that. It is just by experience people have found that.
Okay, so it's manual entry.
Manually entered. Yeah, somebody has just computed and stuck it in. Right? And it's one of those little tricks. First you encounter like, okay, where is this magic number coming from?
I thought it's a learnable thing, so I can make it.
Yeah, in a way, you just take a lot of data and do basic statistics on it, right? Compute the mu and sigma, and you say, okay, there you go.
You say like download the image, any number I can put?
What's that?
You said like you can download the image and put that. What numbers do you use?
Oh, if you take these values, it will work because these values have been computed over a large number of images. And so for any image that you start with, most likely they are good enough starting points. See, your mu and sigma may be different, but not vastly different from these, right? So you can get away with it. That's pretty much the message. That's all it is. So guys, see, I'm getting into the details of the code, right? You will understand this code. There's nothing hard about the code, but you do need to spend time into it. Like for example, this is to visualize the image. I am show, right? You can do that to show the image, or you can just to visualize the image, or you can have your own little utility or whatever it is to render the image. Yeah. If you have some Python library to show the image, just give it the name of the image and it will do it. Right. So you can see that these images in this particular code are very basic images. I'll stop there. Any questions, guys? I hope the basic training loop of PyTorch is looking familiar to it. It's a double for loop. One for loop, outer for loop is for epochs. Inner for loop is for mini batch. What are the four main steps in there? Forward direction. Input goes in, output comes out. Compute of loss, right? Because outputs are the predictions. Now from the predictions, you compute the loss by comparing it to the label. Then you then you take the gradient and back propagate it. That's the backward step. And then the actual step or the learning part of it, right? Optimizing. So optimizing it, yeah. Optimizer will take one step of learning. That's it. And throughout the course, whichever neural architecture we deal with, this is all that it comes down to at the end of it. This is your training loop. So guys, any questions?
When you take the pictures of these images, how do you make that table of image and a label? Are you supposed to do the labels also?
Yeah, you have to do
so how do you like
the simplest way you do that is call the directory, create one directory of weeping willow and one directory of pepper tree. And literally when you load the data, so when you load the data from your thing, remember which directory it came from. That is its label.
Same label for all.
That is it. Yeah, that's a very common convention people follow in this. Just the directory.
Can we use Scotch or something to
You can use Scotch, of course. Use Scotch, PyTorch Lightning, whatever makes your life easier.
The raining and testing
It basically removes this double for loop. It hides it from you. You don't even have to write this code. Actually, see, guys, when you use it, you will realize that to create your solution will be barely 10 lines of code, right? Using these things. So, and then you realize how much power you have accessible to you. Think about it. We are talking about two trees, but in reality, okay, let me make it very real for you. Suppose you're looking at a manufactured part. Is it defective or not? Do you realize that you can use this network as is with fine tuning? You have a box of images of defective parts, one box of images of not defective parts. Does that make sense, guys? Right? Do that. It is used. In fact, we use in support vectors, we specifically solve this problem.
So how big or how heavy this model is? For example, if I want to run it in
CNNs are
not big, right? So basically, if I run it in a Raspberry Pi, it will be that.
Raspberry Pi. Well, it's when I say it's not big,
the
it doesn't
manufacturing
mean that.
defect, so I can put it in
Okay.
Raspberry Pi and
No.
put it into the
You
camera.
can. It works. I think it works there. Mobile net.
Yeah.
Take a smaller version. CNNs work just fine in embedded devices. In fact, they do work now. But I would suggest that guys, for this courses, right, as a baseline, I would suggest get yourself a 4090 if you can't afford a 4090, 3090s have become very cheap. RTX 3090s on eBay, used ones are now available for 650 or 700 bucks. GPU. GPU. So a 3090 RTX, 3090 and NVIDIA, if you look up on eBay, you can get it if you're lucky for 700 bucks. Right. One piece of advice, don't get it from Craigslist.
Oh.
Just last week, one student bought it from Craigslist and somebody gave him a fake and charged $1,200 for a 4090 that didn't work, and it was a fake. So be careful though when you're buying used components. Be careful. Get it from a reputable source. If the price is too good to be true, it probably is too good to be true.
Asif, one quick suggestion that the normalization that you have explained, if you want to clip that into a short video and put it there, that would be awesome.
Sure, I'll be happy to. I'll be happy to. Guys, there was a simpler world once when we didn't have so many architectures. I would start the deep learning course with just feed-forward network, go through all these topics, and end with CNN. Then we used to cover all these things slowly.
Now we are starting with CNN.
Now we are starting with CNN.
Asif, I may have to log off 12:44. We're driving tomorrow. It's our son's 21st birthday. So,
oh, congratulations.
Yeah,
Happy birthday.
Happy birthday.
Good night. Great session, Asif. Thanks, everyone.